How we measure the universe's age and size. How old is the universe? How big is it? These might seem like impossible questions to answer. After all, we can't travel to the edge of the universe or rewind time to its beginning. We're stuck here on one small planet, observing from a single vantage point in space and time. Yet astronomers can tell you with remarkable precision that the universe is 13.8 billion years old, give or take about 20 million years. They can tell you that the observable universe is about 93 billion light-years in diameter. These aren't wild guesses, they're measurements based on careful observations and fundamental physics. Today, we're exploring how we actually measure these cosmic dimensions. We'll look at the clever techniques astronomers use, the observations that constrain these values, and why these measurements are so important for understanding the cosmos. This is a story of human ingenuity, careful reasoning, and the power of physics to reveal truths about the universe on the grandest scales imaginable. The cosmic distance ladder. To measure the universe's size, we first need to measure distances to objects in space. But there's a problem. We can't simply stretch a tape measure across the cosmos. Instead, astronomers have built what's called the cosmic distance ladder, a series of techniques, each calibrated by the previous one, that allows us to measure progressively greater distances. The first rung is parallax. As Earth orbits the Sun, nearby stars appear to shift position slightly against the background of more distant stars. It's the same effect you see when you hold your finger at arm's length and close one eye, then the other. Your finger appears to jump. The amount of shift depends on distance. Closer stars shift more, distant stars shift less. By measuring this parallax angle, typically just tiny fractions of a degree, astronomers can calculate distances to nearby stars using simple trigonometry. This method works reliably out to a few hundred light-years, and with precise measurements from satellites like Gaia, we can now measure parallax for stars up to thousands of light-years away. But the universe is vastly larger than that. For more distant objects, we need brighter markers. This is where standard candles come in, objects whose intrinsic brightness we know. By comparing how bright they appear to how bright they actually are, we can calculate distance. It's like seeing a light bulb in the distance. If you know it's a 100-watt bulb, its apparent dimness tells you how far away it is. One crucial standard candle is Cepheid variable stars. These stars pulsate regularly, brightening and dimming in cycles that range from days to months. In the 19-teens, Henrietta Leavitt discovered that the pulsation period is directly related to the star's intrinsic luminosity. Longer periods mean brighter stars. This period luminosity relationship turns Cepheids into reliable distance markers. By observing Cepheids in nearby galaxies, which we can do with powerful telescopes like Hubble, we can measure distances up to about 100 million light-years. This extends our reach far beyond parallax measurements. For even greater distances, we need even brighter standard candles. Type 1a supernovae provide this. These stellar explosions occur when a white dwarf star accretes matter from a companion until it reaches a critical mass, the Chandrasekhar limit, of about 1.4 solar masses. At this point, the white dwarf undergoes runaway nuclear fusion and explodes with remarkably consistent brightness. Because Type 1a supernovae reach nearly the same peak luminosity, about 5 billion times brighter than the Sun, they can be seen across billions of light-years. By observing these Type 1a supernovae in distant galaxies and measuring how bright they appear, astronomers can calculate distances across a significant fraction of the observable universe. Each rung of the cosmic distance ladder is calibrated by the previous one. Parallax calibrates Cepheids, Cepheids calibrate Type 1a supernovae, and so on. This interconnected system allows us to measure distances from nearby stars to the most distant galaxies. Cosmic expansion and Hubble's law. But measuring individual distances is only part of the story. To understand the universe's size and age, we need to understand that the universe is expanding.
In 1929, Hubble made a groundbreaking discovery. By measuring distances to galaxies using Cepheid variables and measuring their velocities using redshift, the stretching of light toward redder wavelengths due to motion, he found a relationship. More distant galaxies are moving away faster. This relationship, now called Hubble's law, can be expressed simply. Velocity equals the Hubble constant times distance. The Hubble constant, denoted HO, describes the current rate of cosmic expansion. If you measure it correctly, you can work backward to determine when the expansion began, giving you the age of the universe. The expansion isn't galaxies moving through space like shrapnel from an explosion. Instead, space itself is expanding. Galaxies are embedded in space, and as space expands, galaxies move apart. It's like dots drawn on a balloon. As you inflate the balloon, the dots move apart, but they're not moving across the balloon's surface. The surface itself is stretching. This has a crucial implication. There's no center of the expansion. Every point in the universe sees all other points moving away, with more distant points receding faster. We're not at the center of anything special. Every galaxy sees the same pattern. Measuring the Hubble constant precisely has been a major goal of observational cosmology for decades. Current measurements give values around 70 kilometers per second per megaparsec. This means that for every megaparsec of distance, about 3.26 million light-years, galaxies are moving apart at an additional 70 kilometers per second. But there's a complication. Different measurement methods give slightly different values for the Hubble constant. Measurements using the cosmic distance ladder give values around 73, while measurements based on the cosmic microwave background give values around 67. This discrepancy, called the Hubble tension, is one of the most important unsolved problems in cosmology today. Despite this tension, all methods agree that the universe is expanding, and they all give ages in the range of 13 to 14 billion years. The precise value depends on which measurement you trust, but the overall picture is clear. The cosmic microwave background. The most precise measurement of the universe's age comes from observing the cosmic microwave background, or CMB. This is radiation left over from when the universe was just 380,000 years old, and it provides a snapshot of the early universe. In the first moments after the Big Bang, the universe was extremely hot and dense, a plasma of electrons, protons, and photons. The photons scattered constantly off the charged particles, making the universe opaque, like being inside a fog.
As the universe expanded, it cooled. Eventually, about 380,000 years after the Big Bang, the temperature dropped enough for electrons and protons to combine into neutral hydrogen atoms. This is called recombination. Without free electrons to scatter off, photons could suddenly travel freely through space. The universe became transparent. Those photons have been traveling through space ever since, stretched to microwave wavelengths by cosmic expansion. Today, they form a faint glow filling the entire sky, the cosmic microwave background, with a temperature of 2.725 Kelvin, just above absolute zero. The CMB isn't perfectly uniform. It contains tiny temperature fluctuations, regions that are slightly hotter or cooler by about 1 part in 100,000. These fluctuations represent density variations in the early universe, the seeds that eventually grew into galaxies and galaxy clusters. By analyzing the pattern of these fluctuations, cosmologists can determine fundamental properties of the universe with extraordinary precision. Satellites like WMAP and Planck have mapped the CMB in exquisite detail, measuring temperature variations across the entire sky. The key is that the pattern of fluctuations depends on cosmological parameters, the density of matter, the density of dark energy, the expansion rate, and the age of the universe. By fitting theoretical models to the observed pattern, cosmologists can determine these parameters. The Planck satellite's measurements, combined with sophisticated analysis, give an age of 13.787 billion years, with an uncertainty of just 20 million years, about 0.1% precision.
This is one of the most precisely measured numbers in all of cosmology. The CMB also tells us about the universe's geometry and composition. The measurements reveal that the universe is spatially flat. Parallel lines remain parallel at cosmic scales. They show that ordinary matter makes up only about 5% of the universe's total energy density, with dark matter contributing 27% and dark energy 68%. The observable universe versus the entire universe. Now we can address the universe's size, but first we need to clarify what we mean by the universe. When astronomers talk about the observable universe, they mean the region from which light has had time to reach us since the Big Bang. This is fundamentally limited by the finite age of the universe and the finite speed of light. If the universe were 13.8 billion years old and nothing else complicated things, you might think the observable universe would be 13.8 billion light-years in radius, a sphere centered on us with a radius equal to how far light could have traveled in 13.8 billion years. But cosmic expansion complicates this. While light has been traveling towards us, space has been expanding, stretching the distance. A galaxy whose light has been traveling for 13 billion years isn't 13 billion light-years away now, it's much farther, about 46 billion light-years away now. This is why the observable universe is about 93 billion light-years in diameter. The most distant objects we can see, objects whose light has been traveling for over 13 billion years, are now about 46 billion light-years in each direction. The observable universe has a well-defined edge, but it's not a physical boundary. It's simply the limit of how far light has had time to travel. Beyond this horizon, there's presumably more universe, but we can't see it because the light hasn't reached us yet. As time goes on, the observable universe will grow as light from more distant regions arrives. But what about the entire universe, the total size beyond what we can see? Here, we honestly don't know. If the universe is infinite, as many measurements suggest, then it has no size in the traditional sense. It simply goes on forever. If the universe has a finite size with some exotic topology, like a hypersphere or torus, it could be larger than the observable universe, but still finite. Current observations suggest that if the universe is finite, it must be at least hundreds of times larger than the observable universe. But we have no way to measure the size of anything beyond our observational horizon. So when we say the universe is 93 billion light-years across, we're specifically talking about the observable universe, the portion we can theoretically see. The total universe could be vastly larger, possibly infinite. Look back time and cosmic history. As astronomers gaze deeper into the universe, they're embarking on a time travel journey that spans billions of years. The connection between distance and look-back time transforms astronomy into a form of time travel. A 1 billion light-year galaxy appears as it was a billion years ago. A 10 billion light-year galaxy appears as it was 10 billion years ago, when the universe was less than 4 billion years old. The most distant galaxies observed by James Webb's telescope appear as they were just a few hundred million years after the Big Bang. This connection transforms astronomy into a form of time travel. We can't observe the universe as it was yesterday or last year, but we can observe it as it was billions of years ago by looking at distant objects. Astronomers use this to study cosmic evolution. By observing galaxies at different distances, and therefore different ages, we can see how galaxies have changed over cosmic time. We see that early galaxies were smaller, more irregular, and undergoing more vigorous star formation than galaxies today. We see that galaxy mergers were more common in the past. We see how the large-scale structure of the universe assembled over billions of years.
The most distant thing we can observe is the cosmic microwave background itself, emitted when the universe was 380,000 years old. This represents our ultimate look-back time. We can't see earlier because the universe was opaque before recombination. Understanding cosmic age also helps us understand stellar evolution. The oldest stars in our galaxy are about 13 billion years old. These stars must have formed relatively soon after the Big Bang, within the first billion years. Finding stars older than the universe's age would be a serious problem for cosmology, but we don't find any. The ages of the oldest stars are consistent with the cosmic age derived from the CMB. Measuring cosmic acceleration. In the 1990s, observations of distant Type 1a supernovae led to a startling discovery. The universe's expansion is accelerating. Distant supernovae were dimmer than expected, indicating they're farther away than a universe expanding at a constant rate would predict. This discovery, which earned the 2011 Nobel Prize in Physics, revealed that some unknown form of energy, dark energy, is driving accelerated expansion. Dark energy makes up about 68% of the universe's total energy density, yet we don't know what it is. The leading candidate is the cosmological constant, a form of energy intrinsic to space itself. The discovery of cosmic acceleration affects how we calculate the universe's age. If the expansion had been constant, you could simply divide distance by velocity to get age, but acceleration complicates this. The universe expanded more slowly in the past when matter density was higher, then began accelerating as dark energy became dominant. Taking acceleration into account, the age calculation becomes more complex, requiring knowledge of matter density, dark energy density, and the expansion history. This is where the CMB measurements become crucial. They provide these parameters with high precision. Interestingly, if the universe had been decelerating throughout its history, as would happen if only matter were present, it would be younger than 13.8 billion years. The presence of dark energy causing acceleration means the universe is actually older than it would be otherwise. Dark energy has, in effect, given the universe more time to reach its current state. Independent age checks. While the CMB provides the most precise age measurement, it's reassuring that independent methods give consistent results. The ages of the oldest stars provide one check. Globular clusters, ancient collections of stars orbiting galaxies, contain some of the oldest stars in the universe. By studying their properties and modeling their evolution, astronomers estimate ages of 12 to 13 billion years for the oldest clusters. This is consistent with, though less precise than, the CMB age. Radioactive dating provides another check. Long-lived radioactive isotopes like uranium-238 and thorium-232 decay slowly over billions of years. By measuring the abundances of these isotopes and their decay products in ancient stars, astronomers can estimate when these elements were created. This nucleo-cosmochronology gives ages consistent with the universe being about 13 billion years old. The expansion rate derived from observations of distant supernovae and galaxies, combined with measurements of matter density, also gives ages around 13 to 14 billion years. While the Hubble tension shows there are discrepancies between different measurement methods, all methods point to the same general timeframe. This convergence of independent evidence strengthens our confidence that the age measurement is correct. It's not based on a single observation or technique, but on multiple lines of evidence, all pointing to the same conclusion. Limitations and future measurements. Despite the precision of current measurements, there are limitations and ongoing refinements. The Hubble tension, the discrepancy between local measurements of the expansion rate and measurements from the CMB, remains unresolved. Either there's systematic error in one or both measurements, or our cosmological model is incomplete. Resolving this is a top priority in cosmology. Future missions and telescopes will improve measurements. The James Webb Space Telescope is observing the earliest galaxies with unprecedented clarity, potentially revealing new information about the early universe. Future gravitational wave observatories might detect signals from the early universe, providing independent probes of cosmic expansion.
Ground-based surveys like the Vera-Rubin Observatory will observe millions of galaxies and supernovae, refining distance measurements and expansion history. New techniques, like using gravitational waves from binary neutron star mergers as distance indicators, offer independent checks on the cosmic distance ladder. There are also philosophical limitations. We can only measure the observable universe, the region causally connected to us. We can't observe what's beyond the cosmic horizon, so we can't determine if the universe is finite or infinite in total size. We can measure when our observable region began expanding from a hot, dense state, but we can't determine if there was anything before the Big Bang or what might exist beyond our horizon. These limitations don't diminish the achievement of measuring cosmic age and size. They remind us that science is an ongoing process of refinement, where each answer raises new questions. So how do we measure the universe's age and size? Through an interconnected web of observations and reasoning. We measure distances using the cosmic distance ladder, parallax for nearby stars, Cepheid variables for nearby galaxies, Type 1a supernovae for distant galaxies. We observe cosmic expansion and measure the Hubble constant. We analyze the cosmic microwave background, extracting cosmological parameters from its temperature fluctuations. We observe how the expansion rate has changed over time, revealing dark energy's influence. From all this, we determine that the universe is 13.8 billion years old, and that the observable universe is 93 billion light-years in diameter. These aren't abstract numbers. They represent the cosmic stage on which all of history has played out, the arena within which galaxies formed, stars ignited, planets coalesced, and life emerged. What makes these measurements remarkable is that we've determined them from one small planet using light collected by telescopes and analyzed according to physical laws. We can't travel to the edge of the universe or journey back to its beginning, yet we know its age to better than 1% precision. This is the power of science, to reveal truths about reality that aren't immediately apparent, to extend human knowledge far beyond our direct experience. Every time you look at the night sky, you're seeing light that has traveled across billions of light years and billions of years. We live in a universe whose dimensions we can measure and understand. Thank you for exploring these cosmic measurements with me. If you found this valuable, subscribe for more deep dives into how we know what we know about the universe, and leave a comment. What aspect of measuring cosmic scales fascinates you most? Keep questioning, keep measuring, and keep marveling at the cosmos.